Good afternoon. So today we are ready for our next phase of our syllabus, which is we will be talking about optics from now onwards, right? So I hope all of you are ready. So without any further delay, let us begin our topic of polarization of light. So, as we all know, you all have already discussed about, learnt about diffraction of light, interference of light. Now, this interference of light or diffraction of light could be completely explained on the basis of the fact that light was a wave. Light was acting like a wave. However, whenever we say a wave, there are basically two types of wave. I hope all of you will agree with me and will remember that there are basically two kinds of waves. And what are they? They are either longitudinal waves or transverse waves, right? Now, what do I mean when I say that a wave is a transverse wave or a longitudinal wave? Remember that belonging to that particular wave, suppose the wave is traveling along, say, x-axis. If this direction of propagation of the wave is the same as the direction of the oscillation of some waves component, then we call this kind of a wave as the longitudinal wave. The example, the easiest example which comes to mind is sound, where the materials or the particles of the medium travel along the same direction as the direction of the propagation of the sound wave. However, when we talk about light or electromagnetic waves as such, they are not following this particular method. What do they have? Rather, they have their oscillation occurring in a direction which is perpendicular to the direction of propagation, right? So, suppose I have, this is my direction of movement, then this oscillation would be occurring in a plane which is perpendicular to it. It would be, the direction of the oscillation would be perpendicular to the direction of propagation of the wave. This type of waves are called as the transverse waves. And light or any type of electromagnetic radiation actually is a transverse wave. All right. Now, this particular nature or this particular property of the light wave, that it is a transverse wave, could only be discovered or explained when polarization of light was discovered. Okay, before that, it was not known that what kind of a wave is the light, right? So, polarization is actually that phenomena which gave us the information that light is actually transverse in nature. All right. So, now when we have, see, actually polarization, you know, it was discovered in 1690. In 1690, which means in 2020, it is the 390th year. I mean 330th year. We are celebrating the 330th birthday of polarization this time. Right, discovery rather. So anyway, in this scenario, let us now first try to understand that what is the meaning of polarization of light. Why is it able to tell us that the particular oscillation is occurring perpendicular to the direction of propagation? So let us try to first understand what is the meaning of polarization of light. All right. Now, say, as we have already discussed that electromagnetic waves, I mean, light is an electromagnetic wave. So, in electromagnetic wave, if I ask you to think that what is the speciality of an electromagnetic wave, you all will agree with me that in electromagnetic wave, we can visualize the entire wave in terms of, say, like three components. And what are they? Say, if this is my direction of propagation, this is, say, the x-axis. I have along the y-axis the presence of the electric field associated to this wave. And along the third axis, say which is the z-axis, there exists the magnetic field. So every electromagnetic wave is associated with two fields. Remember, the electric field and the magnetic field. And these components of electric and magnetic field each other, and they are again mutually perpendicular to the third to the direction of propagation. So this is how you can visualize the light wave or any electromagnetic wave. Now, in general, when we talk about light waves, or we will be discussing or doing any mathematics related to the light wave, it has been seen that it is the electric field component which actually causes vision, which causes the detection of light in our cornea. So it is not the magnetic field which is causing us to feel the light or to see. So that is why what we generally do is we keep this magnetic component silent. It is there, but it is as if the silent one. Okay, we are not going to discuss about it. But what we are now going to discuss is this electric field, which is very, very important in case of the light waves. All right. So now just think of the situation. Say this is the direction of propagation, and this is the so-called electric component. And as we have discussed, this electric component is vibrating or oscillating along the direction or the plane which is perpendicular to the direction of propagation. Now see, suppose the moment I have switched on the light wave is traveling to my eyes, till my eyes. But what do I have? It may be consisting of one ray or one wave which is having its electric component. If this is the direction of the propagation of light from the light source to my eyes is the same. However, one of the wave might be having, so suppose this is my direction of propagation. One of the light waves has the electric field like this, perpendicular. But there is also a possibility that another light wave, again reaching my eyes at the same time, is having its electric field like this. Are you following me? In this scenario also, the direction of propagation and the electric field are 90 degrees. They are not, they are not breaking any law. This electric field was 90 degree in this case also, in this case also. So when there are large number of light waves which are reaching my eyes at the same time, whose direction of propagation is unique, is the same. However, what is happening? One of them is having an electric field like this, the other like this, the other like this. And this possibility can be that of 360-degree orientation. Are you agreeing with me? That the particular light, the general light, when I switch on the light bulb or I switch on a torch, all these lights are consisting of waves whose electric fields can oscillate along this direction or this or this or this, anywhere. So this kind of a light is called a unpolarized light, where I have not been able to restrict the oscillation of electric field as per my wish. But on the other hand, now please try to understand the fact that by some means, say by some means, out of all these orientations, I have been able to filter out all, and I have kept only this particular component of the electric field, which means the light ray which is coming to my eyes is only having the electric field oscillating in this manner. There is no presence of this or this or this. So, which means I have been able to restrict the electric field vector along only one direction, along only one plane. This is called polarization of light. Are you following? This is called polarization of light. Now, on a very lighter note, when do I call that? Suppose sometimes we are quarreling with our friend and I will say, you are a very polarized person. You are not listening to me. What do I mean by polarized at that time? I mean that that person is only having a fixed idea in his mind and he is not able to listen, or he is not getting my line of thought. So in the same manner, when a particular light source is having only one direction of electric field, at that time I will consider that it is polarized. Right? So is this understood by all of you? That we are able to restrict the electric field of the light rays which are coming to our eyes only to one direction or a one plane. Then this kind of activity or this kind of phenomena can be called as polarization of light. Okay. However, over here I would also like to tell you that when we are able to restrict this electric field only to one plane, this is the best polarization which can be done. This is called plane polarized light. This light will be called as the plane polarized light, which is the best thing which is possible to be done. However, there are other two types of polarization as well. One is called elliptically polarized light and the other is called circularly polarized light. But we will talk about these the circular or elliptically polarized light little later. As of now, I hope all of you have understood or you have got the idea that what do I mean when I say that polarization of light has occurred, right? Is this fine for all of you? Very nice. So once when we have understood what is polarization of light, I would now like to tell you about 2 points or rather two definitions which are very important when we are going to define this polarization. All right. So let us begin from there. So what we are going to start with is, say this is my direction of propagation. The direction of propagation of the particular light wave that we are considering, I have drawn it, say along the x-axis. Okay, say this is the x-axis. Now, as we have already discussed that in case of a plane polarized light, what do I have? I have the electric field vector oscillating only along a particular direction. Say this is this direction. Fine. Now, say this is along the y-axis. In this scenario, all of you please note this, that I can draw a particular plane, say A, B, C, D, which is this plane ABCD that I have drawn over here, see, is parallel to the y-axis, parallel to the direction of the oscillation or vibration, right? And is perpendicular to the direction of propagation. This ABCD plane is called the plane of vibrations. Please note down that this is called the plane of vibration. All right, the plane of vibration. On the other hand, I can also draw a particular plane which is perpendicular to this plane but is parallel to the direction of motion. Please note down this particular plane, say I have drawn it as EFGH. This EFGH is perpendicular to ABCD. However, it is parallel to the direction of propagation of light. This particular plane EFGH is called the plane of polarization. All right. This plane EFGH will be called as the plane of polarization. Why did I think of mentioning this over here? Because there can be small questions, maybe 2-3 marks, where they will be asking you that define plane of polarization, define plane of vibration. So this is what you are supposed to show them. And as I always tell you that whenever these type of questions come, it is always advised that you draw the diagram and along with the diagram, you just write it down. Okay. So I hope all of you have understood these two terms or these two definitions of plane of vibration ABCD and plane of polarization EFGH. So if we have understood this part, let us now move forward to the rest of our lesson. So once we have understood that what is polarization of light, now I would like to discuss about methods of polarization, isn't it? I told you in the beginning that by some means we have been able to restrict the vibration or the electric field vector to a certain plane. But what are those methods? And remember, the methods in this particular module that we are going to discuss are all natural methods. What do I mean by natural methods? Which means these methods are already occurring in nature. These phenomena that we use or are being used are natural in nature. They are not man-made as such. All right. And under these methods, the first method which I would like to discuss is called the method of reflection, which means we can polarize light with the help of the phenomena of reflection of light. All right. So the first thing that we are going to discuss will be polarization by reflection. Now, how is that? Now, suppose I have taken an optical medium, say a glass slab. Okay, this is my glass slab, and I will be incident. What we will make? Will send here on this surface. We will send unpolarized light. Now, before I draw the diagram, it would be very good if I tell you that how to draw or how we generally denote polarized light and unpolarized light diagrammatically. Okay, since in the unpolarized light, the electric field vector is possible, can be there in all the directions. So generally we draw it like this. Something like this. So this kind of figure can be used to denote unpolarized light. Whereas when I am showing a polarized light, a plain polarized light, I will be drawing it only like this. Okay, which means I have restricted the electric field only along this particular direction. So if you see these kind of notations or figures or in the diagrams, I hope now you will be able to understand this. Sometimes it is also drawn with a small dot in this along this, which shows that maybe it is like this, which shows that instead of this direction, the direction of the electric field is like this. Sometimes they also do like this. So these are various methods in which we generally denote the polarized and unpolarized waves of light. Now, as I was discussing about the method of reflection. Now see what I have done. I have taken an unpolarized light and I made it to incident on the glass plate. Alright, so what we have done, we have taken any optical medium and we let the light get incident on the plate. Then what will happen? Obviously, you will agree with me that part of the light would be refracted, right? And part of the light would be reflected. This is as simple as possible. But here it is very interesting to note that when unpolarized light, completely unpolarized light gets reflected from a polished surface like this reflected ray is partially polarized. So I may draw it something maybe like this. So it is not completely plane polarized. Remember, we are just discussing about a method called reflection by which we can polarize light. However, this reflection method only yields us partial polarization, which means not all the components of electric field can be restricted. Arjun, for every wavelength, every color will have difference in glass. Difference in glass by this particular thing. What are you meaning? I did not follow. I mean, like reflection or refraction. You are meaning reflection or refraction. Maybe we can discuss. Now I lost which pen I was writing with. All right. So this is simple reflection and refraction where we have taken unpolarized light. This could be, please make sure, please remember this could be monochromatic light, this could be polychromatic light. Unpolarization of light, the unpolarized factor or the phenomenon of light or the characteristic of light is not restricted only to polychromatic light sources. All right, this can be there for a monochromatic light source as well. Remember, in our laboratories, we use the sodium light source. That is a monochromatic light source. However, that is also unpolarized in nature. All right. It is only that we are not, the electric field vector is rotating in any direction or rotating rather oscillating in any particular direction. So in this case, wavelength factor is not coming in. What is coming in is only the electric field, the oscillation of the electric field. So please remember this part. And I have not even used any prism in this case, where the components of a polychromatic light source might be, kind of dispersing. We are only considering a simple glass slab where simple reflection and refraction are occurring. Okay, so let us not complicate any further. Fine. So as I was telling you, when we study this reflected light, this reflected wave, it is seen that it is partially polarized, which means not all the randomly orientation of electric field is seen. It has been restricted to only a few of the directions. And along with this, as a free gift, this refracted ray is also partially polarized. Are you following me? Suppose we started with 10 unpolarized directions, maybe 4 has been taken over there and the rest of the 10 have been taken over here. So both by reflection as well as refraction, partial polarization of light can be achieved. So is this understood? Okay, I hope Yusuf is now okay with what we are discussing. All right. So as I was telling you that by using the simplest method of reflection or refraction, we can achieve partial polarization of light. Okay, now since these methods, as I was telling you, since these methods are natural in nature, we are not having a lot of control over them. Like I will not be able to completely regulate it as to which part of which electric field I am keeping and all. This is only an observation which I can make. Okay, so this is the method of reflection, as well as in the same thing we can see it is also occurring by the method of refraction. But before I go forward over here, I would like to tell you about a very famous law. The law which is called as the Brewster's law. Now this Brewster's law is basically a very important law because it is used in various types of applications as well. Now, Brewster, the particular scientist, he worked with lots of such optical medium. Okay, he worked with lots of optical medium and he was working extensively by observing this particular refraction, reflection and then polarization of light. What he observed that, see, as I told you that just by, say, this is the angle of incidence and this is the angle of reflection. We all know that angle of incidence and angle of reflection, incidence and angle R are equal to each other. I hope all of you remember this part. And say, so I can call this as I because both of them are same. Whereas this angle of reflection is angle R. We are denoting by these notations. Fine. Now while he was doing the experiments, what he did, he changed this angle of incidence by various values. He changed the values of incidence, angle of incidences, and he noted down this angle of this reflection and all. And he found a very strange effect. He found that for every optical medium like this, there exists a particular angle of incidence, which he called as theta p. Please note down that for every optical medium like this, there exists a particular angle as named by Brewster as theta p, that if the light is incident at an angle theta p, this reflected light is completely plane polarized. Are you following me? That for random angle of incidences, they were only partially polarized. But the moment the particular angle of theta p was used for the angle of incidence, this reflected light was completely plane polarized. And not only that, even more fascinating, that this particular angle, the tangent of this particular angle theta p is nothing but the refractive index of this medium. Are you following? Yes, Yusuf, you are right. We are actually coming into the exact Brewster's law like this, which means for every optical medium like this, there exists a particular angle of incidence which causes plane polarization of light. And because polarization is occurring in a complete manner, that is why the suffix theta p is generally used. And the tangent of this angle theta p is nothing but the refractive index of this medium. Right. Now see, I was telling you that this law can be used for application, right? Why? How can I use this law for application? Because when suppose I want to plane polarize a light, I want to produce a light which is plane polarized. Then what will I do? If I know what is the refractive index of the medium that I am going to use, I can calculate what will be theta p and I will be incidenting the light exactly at theta p. Isn't it? So like this application of this Brewster's law has very important application for the purpose of applying or polarizing of light. Alright, so this is what is the so-called definition of Brewster's law. There is a very important corollary attached to this particular thing as well. And what is that? Now let me just show that to you. Say, if this is theta p, I hope all of you will agree with me that this is also theta p. And because we are using the particular notation of theta, let us call this angle of refraction as theta r. Alright. It was also seen, or rather it can also be proved from this particular law, that the angle between the reflected ray and the refracted ray, the angle between the reflected ray and the refracted ray is 90 degree. Alright, are you following me? This follows as a, what to say, a corollary or a sub-result of this tan theta p is equal to mu. And I am going to now show you how, because this generally can be asked in the examination. Alright, so now let us do this particular small derivation. We will begin with here only. Tan theta p is equal to mu. Now can I not write tan as sin theta p by cos theta p? You all will agree with me. However, now if I ask you to remember what is Snell's law tells us that the refractive index of the medium is nothing but the sine of angle of incidence by cos, sine of angle of reflection, right? So see, mu is equal to sine theta p by cos theta p. Again, mu is equal to sine theta p by sine theta r. So when I equate these two, what is coming out? It is seen that cos theta p must be equal to sine theta r. Agree? So when I write this, cos theta p is equal to sine theta r, it will be easy for us to compare if I change this cos into, or this sine into cos, right? What I can do? I can change this sine into cos, which means what? Which means I can write this as cos of 90 minus theta r. Am I right? So in this scenario, when we are comparing these two, I can very easily write that this theta p is nothing but 90 minus theta of r. Now please note down, if theta p is equal to 90 minus theta r, what am I getting? Theta p plus theta r is equal to 90 degree, correct? Which means which angle? This angle plus this angle is 90 degree. And if you note that this total is 180 degree. From here to here, total is 180 degree. Whereas this angle and this angle when added is giving me 90 degree. Which means what will be the angle of this? What will be this angle? 180 minus 90 and hence 90 degree. Right? It's very nice. You all are giving me the same feedback that you all have also followed this. So, in the examination, if they are asking you to prove that if the angle of incidence is theta p, or if some light is incident on an optical medium at the polarizing angle, show that the reflected ray and the refracted ray are at 90 degrees, you can very easily show like this. Correct? So I hope all of you have understood about Brewster's law. Proof of this can be given. You will be asked, maybe you will be asked to write down or state Brewster's law, and there can be small little numerical problems as well. Okay, say I will tell you that the refractive index of glass is 1.53. Calculate the Brewster's angle, and so on, and maybe a little bit more of complicated numericals as well that we will be discussing or we will be doing later on. So if this part is understood, now let us move forward to another method of polarization which also occurs naturally. Alright. So I hope I can go forward. Yes. Okay. Now this new method or the next method which I am going to tell you, which can also polarize light, is a very fascinating one. You know, it is called something like double refraction. Double refraction, or sometimes also called bifringence. Bifringence. I think in your school days also you may have discussed all these stuff. We are just taking a recap of all this. Now, what comes to our mind when we hear this word double refraction? What is happening? Why are we calling a particular phenomena as double refraction? Now, see, our nature is very fascinating. It has given us such, I mean, like so many interesting things to observe and realize their importance. Say, generally, when we talk about the optical media, say glass or something like that, what we consider, what do we see? We see that, say, if this is my light, this is my optical media, I send in some light over here, and what will happen? It will be little bending, and then it will be emerging out. It will be emerging out like this. So, this will be the path of light from a general optical medium. So what do I see? When I draw a picture like this, a diagram like this, I see that I have sent in one ray and I have received one ray only. This is normal refraction. However, there are very strange materials, optical materials found naturally in this earth, which have a very nice, or what to say, magical power, that when I send in one light ray into this medium, instead of getting only one ray out of it, we get two rays coming out of it. Isn't it very, I mean, like very surprising and very interesting? So, because we are sending in one particular ray and we are getting out two rays out of them as refraction result, we call this phenomena as double refraction. All right. And there are materials like calcite, which can actually do this particular magic, so-called magic, on their own. Right. So it is not, I mean, it is as if the human beings haven't designed this. The nature has designed this on its own. Right. So this method is called double refraction. But why am I telling you about double refraction in the chapter of polarization? Because it has been observed that these two rays which have come out after being doubly refracted are plane polarized. Both of them. This is also plane polarized. This is also plane polarized. But remember, before I tell you more about it, I would like to add a little point over here, that these two rays that have come out as a result of double refraction, one of these rays follows all the laws of refraction. Reflection, refraction, Snell's law, this and that. So this ray is called the ordinary ray or O ray. Whereas the other ray is not going to follow any rules. It is like some of those students who say, I'm not going to follow any rule, man. I will do whatever I like. So these are the extraordinary rays. This ray, which will not follow the laws of reflection and refraction, these are called extraordinary rays, and we denote them as E rays. Okay, so as a result of double refraction, we are getting an O ray and an E ray. And as I was telling you, this O ray as well as E ray are both plane polarized. But the very fascinating fact is, suppose the O ray is plane polarized in this direction, then the E ray will have a direction which is perpendicular to it, in which the electric field will be oscillating. So not only plane polarized individually, O ray and E ray, the plane of this particular vibration is also perpendicular. So plane of vibration for this, if this is along this direction, this will be along a 90-degree perpendicular direction. Alright. So this happens. This is called double reflection, double refraction, or called bifringence. So this is also a naturally occurring phenomenon. Here, I would like to tell you about two very small points which I have seen to be, coming in the examination. What is that? Now, these crystals which can cause double refraction are also, they can also be classified into two types. And what is that? Now, see, as I was telling you that when O ray and E ray have come up, which means this particular ray has got they have divided themselves into two. So some phenomena has caused these two particular rays to divert from each other. Now what happens? Because of that, this O ray will be having a particular velocity of its own, and E ray also will be having a velocity of its own. When it is coming out, I will suppose I am doing some experiment on the O ray and the E ray. I can find out the velocity of this. Now it has been noted, it has been seen that in some of the crystals, when we are using that particular crystal to polarize light, the velocity of the O ray exceeds the velocity of the E ray. Are you following me what I said? Velocity of the O ray is greater than the velocity of the E ray. These type of crystals are called positive crystals. Please note down that the crystals which after double refraction show that the velocity of the O ray is greater than the velocity of the E ray are called as positive crystals. Whereas in the scenario when velocity of the extraordinary ray is greater than the velocity of the O ray, it will be called as the negative crystal. Now I have a very funny method by which I remember this. That how can I remember that in which positive crystal or negative crystal whose velocity is more? I always tell the same example to all my students, which is think of a society, right? In a society, there are two types of people. One are ordinary people who follow rules, who abide by rules and do everything as per the rules. We are all ordinary people. And there are some extraordinary people who do not follow any rules, they do whatever they like. So, those extraordinary people and ordinary people like us. Now, in a society, which society will you think is a positive society? Where the ordinary people, the rule-abiding people will be doing better than those extraordinary people who do not follow the rules. So, when rule-following people or the good people do better than the bad people who do not follow rules, obviously that society will be a positive society. So, in the same manner, in a crystal, if the velocity of the ordinary ray is greater than that of the extraordinary ray, the ray which does not follow rules, this will be a positive crystal. Whereas, in the just like the society where the bad people are doing better than the good people, I will call that society as a negative society. So, in the same manner, if the velocity of the extraordinary ray is more than the velocity of the ordinary ray, I will call that crystal as a negative crystal. So, this is how I remember, and you can also use the same method in order to remember this particular concept. Okay, so if this part is done, there is a very small thing which is still left, which is another method which is called scattering of light. You know, scattering of light can also produce partial polarization of light. Now, say light is coming from a faraway place to me. It is going to, it will be scattered by those small little particles, the dust particles, which is prevalent in the air around me or the medium around me. So the light will get scattered. That scattering also causes partial polarization of light. So if I have to count what are the methods by which naturally light gets polarized, reflection, refraction, double refraction, and scattering also can be mentioned over there. However, since this is completely unorganized, I will not be able to control this. Scattering does not find very big application in the society as such. Okay, so that is what brings us to this is about what we have to study about polarization, the methods of polarization in our syllabus. Now, remember I was telling you in the very beginning that there are actually not only plain polarized light, but there is also the presence of or the possibility of something called a circularly polarized light and elliptically polarized light. Now I would like to tell you about those. That what do I mean by a circularly polarized light? What do I mean by an elliptically polarized light? And actually what is the mathematics behind it? Okay. So can we go forward? So if you have understood all these methods, then let us move forward to understanding the concept of circularly polarized light or elliptically polarized light. Okay. Now, see, maybe when we are doing this mathematics to find out or understand what is circularly polarized light or elliptically polarized light, in our syllabus or in our examination that may not be asked to you. But still I am explaining this to you so that you get the concept very, very deep in your mind that what is the meaning of that. Alright. So now what we are going to discuss is circularly polarized light or elliptically polarized light. Now, if I tell you, say how can I write? When we are talking about the mathematics of a light wave, we have to first write down the light wave as such. Now, light wave as usual can be written as say E is equal to, since we are writing it in terms of the electric field vector, we will be writing as some E equal to E0 with this, say we are writing with a sign function. Sign. Now, electric field vector, as we all know, depends on the position as well as depends on the depends on time as well. Now, in general, for a three-dimensional thing, it can be written as this. See, k dot r. I have written it as k dot r, where k is our propagation number, propagation vector, and r is the position vector, right? Which constitutes of x, y, and z. However, if I want to like simplify the entire thing and I want to write as if it is only moving along say x-axis, then what will I write? I will only have the component kx. Kx and x, if I don't want to write even this x, it is generally written like so, like this. Alright. Now, the very important thing which I would now like to tell you is while we are doing the mathematics of this polarization, it has been observed that this position part does not play anything in it. This position part remains silent. Okay, so in this total phase part of my sign, this total angle part of my sign, it has been seen that it is it is this time part, this omega t part, which is important for us to consider. So in this scenario, what we will do, we will keep this part silent. We'll keep this part silent, and just to show you, because I am just trying to show you the mathematical analog of how to create a circularly or elliptically polarized light, it will be enough for us if I write a particular thing, a particular light wave as E0 sine omega t, where E0 is the amplitude, is the maximum displacement of the electric field vector possible. Alright, now beginning from here, let us go forward, let us move forward. Now, what is Yusuf saying? Will the ordinary ray be observed constant in all direction? I did not follow your question, Yusuf. Constant in all direction means? Say this is my optical medium. I have sent an incident ray over here and I have got an O ray and an E ray. I mean, now you are saying that it will be observed in all directions or not? It will be observed in all directions. Why not? Okay. I mean, like, if you send me your question little elaborately, we will discuss about it. Okay. Let us not, kind of take the class even more. It is already 44 minutes. Okay. So now let us move forward with this. So say I am considering a particular light ray, something like this. Now I would ask you all to think about two light waves. I am asking you all to think about two light waves. One is moving along the x-axis and the other is moving along the y-axis. They are mutually perpendicular to each other. Alright. So one of the waves which is moving along the y-axis and the other is moving along the z-axis like this, and say they are meeting at one point. What will happen then? One of the light waves along y-axis, the other wave along x-axis, which means I am asking you all to consider two light waves mutually perpendicular to each other, which are traveling mutually perpendicular to each other and meeting at some point. So say I will consider this as, in order to kind of minimize the entire kind of complication, let me write this as, say there is one wave which is moving along x-axis, a sine omega t, and there is another wave which is y, which is b sine omega t plus phi. Yes, Yusuf, the question that you have asked is what type of crystals this will occur. Now, please remember, if I have to tell you about this crystal has to be, it cannot be an isotropic crystal, which means it will not have the same construction throughout the crystal. These type of crystals are called anisotropic crystals, and the example that I gave you was a calcite crystal. It is not that every medium as such or any crystal that I come across can give us double refraction. These are special crystals. Okay, so example is calcite, and the nature of these type of crystals is anisotropic in nature, which means they are not same throughout the entire structure. Okay, fine. So now, as I was telling you, let us consider two waves, one traveling along x, one traveling along y, and now I have superposed them, which means now they have come and they have met. What will be the resultant? What will be the resultant? This is what I was trying to tell you. However, before I begin, just see what I have considered. These two light waves, these two waves that I have considered are having different amplitudes and they are having different phase. However, I have kept the omega to be constant. Omega to be constant. Why have I kept the omega to be constant? Which means omega is having time period. Time period is related to the frequency, which means I have used waves which are having the same frequency. So if I consider that to be light, both these light waves that I am considering are actually having the same frequency. It is not like that in this scenario I am like, kind of superposing a yellow light with a red light. I am superposing two reds or two yellows. Okay. So we are doing a very, very simple mathematics in this case. So what this is, x is equal to a sine omega t and y is equal to b sine omega t plus 5. So one of them has come from here and the other has come from here. Now what will be the resultant? I want to know what will happen to the wave which have superposed over there. Now let us see and understand the concept. So from here, can I not write that x by a is equal to sine omega t? I can write. Now see, in this, from the second equation, what I will do? I will bring this b over here and I will write y by b is equal to sine omega t plus 5. Now it is as if sine a plus b. So I am going to open up this as sine omega t cos phi plus cos omega t sin phi. You all will agree with me that man has not done any mistake. Correct? Now what I will do, I will take the help of the first equation from where I had found out that sine omega t is x by a. Right? So I'm going to take that x by a from there and I'm going to put the values in the second equation. Okay? So this sine omega t can be conveniently replaced by x by a. However, if sine omega t is x by a, I hope all of you will agree with me that cos omega t is 1 minus x square by a square. Right? Am I right? So all I have done is I have written the value of y by b as x by a cos phi plus root over 1 minus x square by a square sin phi, where this under root term is nothing but the cos omega t part. Correct? So I hope everybody has understood. Nice. So see, I am having a particular equation where I have two terms with no root and one term with a root. So what I will do, I will take this no root term to the left hand side and then we will square both the sides. Right? So what I can do is y by b minus x by a cos phi whole square must be equal to 1 minus x square by a square. Since I have done a square over here, I am having a sine square phi. Correct? I hope everybody can see it clearly. So from this scenario, let us just write the part of the left hand side. Let us see what is there in the left hand side. So is it not y square by b square plus x square by a square cos square phi minus 2xy by AB cos phi equal to the right hand side. Correct? Now please note down, all of you, please note this fact that in the left hand side I have one term with x square by a square cos square phi, whereas in the right hand side I have a term x square by a square sine square phi. Are you following what I am trying you to understand? That if I bring this minus x square by a square sine square phi to the left hand side, what will I be having? Sine square theta plus cos square theta is equal to 1. So following that, if I bring this term in this left hand side, all I will be left with is this term. Did you all follow what I have done? I have brought the x square minus x square by a square sine square phi to the left hand side, and that has given me, then I have added it with the cos square term, and that has given us only x square plus a square. Correct? Very good. Very nice. All right. So in this scenario, just hold on. Let me just write it little nicely. Then we will discuss. So x square by b square plus y this minus 2xy by ab. What was that? Cos phi is equal to sine square phi. This is the equation where we are standing. Now hold on over here. All of you, please tell me, is this equation looking familiar to us? Isn't this equation looking familiar to us? And what is this equation? This equation is nothing but the equation of an ellipse. Remember the equation of an ellipse? And what kind of an ellipse is this? Suppose I have an ellipse whose semi-major axis is 2a and whose semi-minor axis is 2b. Then if I could draw it like this, right? This is the ellipse. This is the equation of the ellipse which I have got. Which means, all of you please note down, what were we doing? What did we begin with? We had superposed two light rays which were traveling in perpendicular directions, and I asked you what will be the resultant. The resultant will be simply an elliptically polarized light. Which means in this case, what will happen? The electric field vector, the electric vector which we were seeing that could only oscillate along this direction or this direction or this direction, what will it be doing? It will actually be moving like an ellipse, where its amplitude will be increasing, will be maximum in this direction and will be minimum somewhere in another direction. Are you following me? And this cos phi that you can see is nothing but this angle phi by which it has inclined along the semi-major or semi-minor axis. So in this case, what I have tried to show you is that actually when I mean, what I mean by elliptically polarized light. Elliptically polarized light actually arises by the combination of two components of some two light waves which are actually mutually perpendicular to each other. And as a result, the electric field vector, you know, it moves in such a manner that it as if it is tracing the path, the trajectory of an ellipse. Alright. So this is the physical meaning, or this is the meaning of elliptically polarized light. So that it is not oscillating only along this direction or this direction. It is oscillating like an elliptically. The path is an ellipse. Okay. Is this understood by now? Now over here, I would like to, kind of play with little bit of these numbers. And I hope all of you will be agreeing with me. You all will enjoy with me. If I now ask you, what will be the value or what will this equation look like if the value of this phi is 0? Which means, remember we began with a phase difference of phi between the x and the y. What will be the scenario if the phase difference is 0 or 2 pi or 4 pi as such? Tell me, what will be the value? In case of phi is equal to 0, sin phi will be 0. Then I will be having this right hand side as 0 and cos phi will be 1. So I will have this. Now what are we seeing in the left hand side? What is this? This is nothing but y by b minus x by a whole square is equal to 0. Am I right? So in this scenario, what is the meaning? If the square is 0, I can also write this is 0. Or can I not write y is equal to b by a into x? I can write this. Now if I ask you y is equal to a constant into x, what is this equation? You all will readily tell me that this is nothing but the equation of a straight line. The equation of a straight line which is not even having any plus c, which means it is passing directly through the origin. Which means from the concept of elliptically polarization, the moment the phase difference between these two was 0, what has happened? The resultant is now a straight line, a simple straight line whose slope is given by b by a. Isn't it? So here now we can see that this is simply plane polarization of light. Correct? And the direction of the plane polarization is this, and the angle, this particular slope is being given by b by a. So we began with what is plane polarization of light, and mathematically also now we can see that how plane polarization is occurring. Yes, very nice. All of you are doing the perfect mathematics. I'm very happy over here. So now see, this was the scenario. So we got a plane polarized light when the two light sources, the two waves that we considered, we began with, did not have any phase difference or a phase difference of 2 pi, 4 pi, 6 pi, 8 pi and so on. Now tell me what will happen. Let me go back to the equation once again. Y square plus b square, x square by a square minus 2xy cos phi is equal to sine square phi. Now the particular condition which I want you all to understand or think upon is what will be the value or what will be the scenario if phi is equal to pi or 3 pi or 5 pi or numbers. Now see, once again, this is going to be 0. The right hand side is going to be 0. But what will be the value of cos phi? The value of cos phi will now be minus 1, which means I'll be having a plus here. Isn't it? So in this scenario, what I am getting is x by a plus y by b whole square is equal to 0. And from here, can I not write that y is equal to minus b by ax? So if I ask you to plot the same thing on this diagram, what will you see? This is also a plane polarized light. However, because this is coming with a minus, this is this kind of a plane polarization, the opposite. If initially we had it as an inclination towards the positive, now it is just having an inclination towards the negative thing. Very good. Very good. So yes, indeed, you all are giving me the right answers. So in this case, are you following? This is how various types of polarization occurs, and it occurs naturally. Fine. Now the last thing which I want you all to show would be the circularly polarized light. Now before I go into circularly polarized light, the condition which I want you all to understand and tell me about is when this phi will be 90° or pi by 2. This was sine square phi, right? I want you all to concentrate on the value of pi by 2. Phi is equal to pi by 2, 3 pi by 2, 5 pi by 2 and so on. Then what will I have? Now sine value is going to be 1. However, cos 0 is going to be, cos pi by 2 is going to be 0, and this term will be put to 0. So what do I have? I have y square by b square plus x square by a square is equal to 1. And what is this? What is this equation? This equation is also the equation of an ellipse. However, as if this ellipse is no longer inclining. It is the one which is straight. Fine. In this scenario, we are also getting an elliptically polarized light, but without this incline factor, as if it is now completely, kind of straight. And finally, now I want to bring you to the condition that what will happen if A and B are same. That is, if the amplitudes of both of these will be same, A is equal to B, what will I get? Can I not then write that x square plus y square is equal to A square? And what is this equation? A square plus this x square plus y square is equal to A square is the equation of a circle. A circle, which means A is equal to B. This is the circle, right? So this particular factor, when phi is equal to pi by 2 and A is equal to B, brings us to the condition of circularly polarized light, where not only the electric field vector is, kind of tracing the path of a circle, the radius is not changing. In the elliptically polarized light, it was tracing the path of an ellipse, and its magnitude was going on increasing or decreasing depending on the path. And in case of a circularly polarized light, what is happening? The radius is remaining the same, right? So now I hope all of you have understood that mathematically what is the meaning of circularly polarized light, elliptically polarized light, or the so-called plane polarized light as well. Fine. So that is all I had to tell you about polarization of light. So if I summarize the entire class now, what all we have seen? We have seen what is the concept, what is the meaning of polarization of light. We have discussed the plane of polarization and the plane of vibration. We have discussed few methods of polarization which are all naturally occurring, and then we have mathematically derived, or we have mathematically seen or tried to understand the meaning of circularly polarized, elliptically polarized and plane polarized lights. So that is all for today, and that is all about polarization of light. So see you all again in the next class. Bye bye.